Hello, today we're going to be talking about Formula FSAE suspension design. Specifically, we're going to find the loads for the 6 suspension tubes in each corner. We're going to do that starting with given accelerometer data, the lateral and longitudinal G's, and we're going to work our way through to get the loads in each arm. Now these loads can be used to design the tubes themselves as well as the wheel assemblies and any mounting on the chassis side. Now to start our analysis, the first thing we're going to do is a simple 2D simplification. And you can see this through the front plane. We've taken a slice to the front plane of our vehicle. And then we're going to do a free body diagram. Because we're taking a slice, we only assume for 3 suspension tubes at the moment, and we'll get into the rest later. Now for a free body diagram, we're going to look at our basic equations, and that's going to be sum of forces in the y direction equals 0, sum of forces in the z direction equals 0, and sum of moments in the x direction equals 0. You can see our coordinate system down here.
Also, because we have pin connections, that's the spherical bearings at the end of each of the 6 tubes, these are all 2-force members, which means that they will only transmit forces axially, which will be very important later.
A few housekeeping items to take care of. If we mount our push rods or toe links to a control arm, that will increase the loads in that control arm and can increase bending loads. This is not going to be looked at in today's presentation. Second, our loads will change significantly depending on geometry. The geometry I've selected for this presentation is made up, and yours will vary differently, specifically depending on if you have a pull rod or push rod and if it's attached to the upper or lower control arm. The point of the geometry shown here is so that you can check your own calculator and make sure it's working properly. I do want to warn you that some teams will use simple trigonometry or similar triangles on their own to just determine the push-pull rod forces. This is very incorrect and often can be off by up to a factor of 2 or more. Finally, I'm going to start with a 2D simplification, but the cleanest and fastest way will be shown at the end for 3D. Finally, a disclaimer, I am neither affiliated with nor endorsed by FSAE, Formula FSAE, and this presentation is not prepared by a professional engineer. However, for our 2D example, we're just going to look at these 3 arms here. So that's the upper 4 control arm and the lower 4 control arm, as well as the pull rod. This here is an example of where our pull rod is attached to our upper control arm. So this is going to introduce additional forces that we wouldn't otherwise see in our upper control arm. They're not going to be analyzed in this presentation. So in our 2D example, we're looking at, if you look at our coordinate system here, y is left, right, and z is vertical. So we have the y, z coordinates for all of our points. These are kind of made up, so they won't make a lot of sense, but they're roughly in the shape of a Formula FSAE car. Now I'm going to assign these letters. So our pull rod is going to be A, top control arm is B, and the bottom one C. And then each of these will have a y, z coordinates. Now, if we look at this geometry, we're going to use these 3 equations up here to determine all the forces in our 3 control arms. We can work out our delta y, delta z, and the length of our control arm just using the x, y, z coordinates of both. Which is quite simple and just use Pythagorean theorem. Now, from similar triangles, we can work out for our force vector, which will be the exact same triangle as our physical geometry. By similar triangles, if we know F, we can work out the y and z components. So we'll do that here with these equations. A quick note, if you're in 3D, then this here's what your length will be, and then we'll also have the fx component as well. So now we'll go back to our 3 equations. Sum of forces in y equals 0, sum of forces in z equals 0, and sum of moments in x equals 0. So we've just done for our first arm A using the equation we just did. And one thing is we don't know FA, which is the magnitude of the force in arm A. And I'm highlighting the knowns for you in yellow here. And then we're going to repeat the same process we did for FA. We're going to repeat that for arms B and C. And we also have an FY applied, which is our force from the tire on the ground at the contact patch. And then so sum of forces in the y direction will equal 0. And then we're going to repeat this process for Z. For moments, things are going to get a little trickier. We're going to go back to our moment equation. This is from Wikipedia. They use tau, I use m. But the moment is the light blue vector up here. And it's a vector, and its r, so r is the length of our wrench, and then f is the direction vector of our force. So it's r m or tau is equal to r cross f. So when we go back to our 2D example here, we're going to introduce r, which is the vector. You can pick any location you want to take moments about. I've used the origin for simplicity. And we're going to put r as Cartesian coordinates here, just to make things a little easier for ourselves. And then we're going to do the same thing for f. So for f, we're just going to break it out into our Cartesian coordinate multiplied by the magnitude of our force vector, which is our unknown. An interesting thing here is that our Cartesian coordinates is actually the unit vector multiplied by the magnitude of the force f. And this will come into play later and make our lives a lot easier. So when we do r cross f, see at the moment, I'm not going through all the math for a cross product here. We're just going to call it mx. And then if we did it in 3D, then this force would actually create a mx, my, and mz. So we'll go back to our equations here. We can now fill in for mx, and now you'll see that we have 3 equations, 3 unknowns, and I've highlighted all of our unknowns for you there. So this is a linear system, which means that we can solve it quite easily. We're going to throw it into a matrix format, and then this takes the form of ax equals b, where x is our unknowns, highlighted in yellow again. I want to highlight again how the unit vector is vertically in the first column, and then to solve this, we'll rearrange ax equals b. We'll rearrange it into x equals a inverse times b. I want to highlight to anyone that's a little rusty on linear algebra that you cannot do x equals b times a inverse. It has to be a inverse times b. The order is important, unlike traditional multiplication. Now, if we switch to 3 dimensions here, you'll see that we end up with an extra row up top, which is sum of forces in x equals 0. We'll end up with 3 additional columns, which are for the 3 additional arms that we will have that we ignored. And then we'll end up with 2 more rows at the bottom for the moments in y and moments in z equals 0. We're going to have 3 more unknowns, which is the force in the 3 arms, and then we'll have 3 more, not shown, we'll have the 3 more applied forces as well. Just to summarize things here and to kind of merge the understanding between 2D and 3D, we're going to have all of our unit vectors, which will be 1 column, 3 row vectors, and then we'll have 6 of them in red, and then at the bottom for all of our moments, in 3D we will have 3 rows and then 6 columns. And this is what it's going to look like manually. And again, it's in x equals a inverse. It'll be solvable with x equals a inverse b. I just want to show this one more time because when we go over to Excel and solve this, this is the way we're going to be doing things. So you can clearly see for 3D, a is our unit vector for a, and it's a 1 column 3 row vector. And then in purple below, r cross a hat is 1 column by 3 row vector as well. The last thing we have to do is determine all these applied forces. Fx, Fy, Fz will be easy. The moments will require a few additional steps. So there's many different approaches you can take. In mine, just because accelerometer data is very available to most teams, I've decided to do it based on that. We need a few vehicle, mass of car plus driver, the height of the center of gravity, which is h, track width, and wheelbase length. So that's track is the center of the tire on the left side to the center tire on the right side. If they're different, you can take an average. Again, we're doing simplifications, and the wheelbase is the distance from the front wheels to the rear wheels. We're going to assume some accelerations, and then ultimately we're going to end up with a list of different load cases, and that's going to be a list of all the different accelerations under hard braking, lateral acceleration, etc., etc. Also note is that when you're using your accelerometer data, you should be filtering it roughly at 10 hertz. So first thing we're doing is going to calculate weight transfer. So we have weight transfer, that's WT lateral, and it's going to be these equations here. One thing I want to remind you is, so these pictures are from MathCAD. If you're doing it in Excel or basically anything else, don't forget to multiply by 9.81 meters per second to translate our 1g into an acceleration. Another thing is I don't have static weight distribution in here, and for additional accuracy, include that as well. So we're just going to, after we calculate our weight transfer, we're going to calculate the FZ applied force on our tire of interest. Now, the way I'm doing this for Fy and Fx is we're going to assume, we know the total Fy of the car, that's the second line, and then we're going to basically apply our Fy based on which percentage of our total FZ that our tire of interest has. So in this case, our tire of interest has 43% of the total downward force of the vehicle, so total weight of the vehicle without an arrow. All this is assuming no arrow. And then if it takes 43% of the vertical force, we're going to assume it takes 43% of the lateral force. Again, this is a major oversimplification, and I encourage you to come up with better assumptions. So for Fx, Fy, Fz, we can now calculate all those three, and for our moments, we need the location of the contact patch. This is a simplified one. All my MathCAD comments that don't actually do anything are shown in light green here. And this is just the simpler way you can do things, and it's just going to be R cross F, just like we were doing before, and that'll get you the applied moments. Now, I like to break them up, and this way we can apply the forces at different locations. This is for two reasons. One, if you want to have like a pneumatic trail in there, you can apply the Fy at a slightly different location, as well as when we get into drive shafts, there's a trick we'll do where we'll move the Fx forces location. So here we'll calculate them all separately, and then we can just add them all together at the end.
The tire also creates a self-aligning moment, which you can analyze if you have TTC data, and then you would add it in here. Unfortunately, it's not shown.
So most FSAE cars have drive shafts. These are most often used to transmit torque from the motor or engine to the drive wheels, the rear wheels. However, there's many different incarnations. As for braking, most vehicles have outboard brakes, which is the rotor and caliper on the wheel assembly. However, a few have inboard brakes, which is one large rotor and caliper on the inboard, and all the braking torque is transmitted through the drive shafts. In either case, this is only applied when torque is being transmitted through the drive shafts. So for most cars, that's just during acceleration. And this torque needs to be accounted for because it's applying torque onto the wheel assemblies, which is what we're doing our free body diagram on. So the torque it's going to apply is equal to Fx times the loaded radius of the tire. And the loaded radius is simply just when the tire is under normal load, it'll compress a little bit. And the quickest way is that we add an additional moment, which should cancel out Fx times the loaded radius of the tire, and we'll just add that into our other applied moments. However, it can be a little tricky to determine if it's positive or negative, which is why I prefer the alternative strategy. The alternative strategy, all we do is we add in the loaded radius of the tire to the Z contact patch, just for Fx, not for Fy and Fz. And all this does is it'll apply in our free body diagram, it'll apply Fx at the height of the hub, and that way it'll apply no torque to the wheel assembly. One thing to be cautious of is that here we're modifying it in the Z. We're modifying the Z height, whereas previously our moment when our drive shaft is in the MY component. So just make sure you do those correctly. You will notice that so in this case, the sum of the moments is the same in both cases. Again, this is only done when torque is going through the drive shafts. Now we need our list of load cases. Again, I've used accelerometer data just because it's available to most teams. You should, again, filter it to 10 Hertz or something better if you've figured that out. These should all be conservative. We want our maximum load cases, we want it to be typically higher than what we'll actually see. We have our normal load cases, which I've designated for fatigue, and then kind of our one-time maximum for yield buckling compression down here, which are more rare cases which might not be seen on accelerometer data, and sometimes I just round it up by a factor to kind of estimate what the most the car will ever see. The weight transfer calculations will be next, and I'm going to have to overwrite those for a few load cases. Like we have our inside wheel on cornering with no weight transfer, as well as for reverse braking, it'll be opposite, and it'll be similar to acceleration. Reverse braking is very important because we end up with weight transfer. It's similar to acceleration, except because all four wheels are causing grip, we'll get more weight transfer, which can cause even higher loads on the rear wheels. Now let's go into how we're going to solve this in Excel. Overall, we're going to stick to our x equals a inverse b formula, which is actually quite easy and uses built-in Excel formulas. However, we're going to write 3 additional functions in VBA, which are going to make our lives easier. And this is a magnitude function, a unit vector function, and a cross product function. One thing I want to note is that all these functions only work on 1 row, 3 column vectors. They don't work on the opposite. And also when you use them in Excel, you have to do an array equation or matrix equation. So when you enter it in, you have to highlight all the cells it'll be entered to and hit Control-Shift-Enter. Hi, so now we're in Excel, and I've pre-populated it with our XYZ coordinates from CAD. And then we're going to go through, as well as our contact patch locations where the applied forces will be applied from the tire on the ground. And we're going to walk through how to solve this in Excel. So first thing we're going to have to do is open up, we're going to have to go File, Options, Customize Ribbon, and we're going to make sure that the Developer tab is checked off. And that way it will appear up here, and then we can go to Visual Basic. So once we've opened up VBA, we're going to right click on our project, we'll insert module, and then I'm just going to copy and paste the formulas in here. Back in Excel, we'll select the 3, we can do equals unit vector, and then we're just going to do the delta y, delta x, delta z all at once in here. So we're going to select our second point, and then we're going to subtract it from our first point. And then we're going to hit Control-Shift-Enter because it's a matrix equation. There we go, and then we can just copy that down for the remaining ones. And we'll just double check that it's correct, and we're good. Now for our moments, in our PowerPoint we picked the moment about the origin, and for our Excel we're going to let us pick the moment anywhere. It shouldn't make a difference to our outcome, and it's a good little check to make sure if we change this, then our outcome doesn't change at all. Now I'm going to take our inboard point and subtract the location that we're taking moments about. In this case it's the origin. And then we're just going to copy this over. Oops, we need to make sure that we have a dollar, that we anchor this in with a $sign there. And we're just going to copy it all the way down. And we're just going to change this one to be the location for our applied forces. And then we can copy these over as well. Now we're going to get into our applied forces, and we're going to have a VLOOKUP here just because we have a lot of load cases down below here, which I've pre-populated. And then this is our load case number here. So right now we're set on load case 2, which is just static. And we're going to type in a VLOOKUP. We're going to use our lookup value as this one. We're going to anchor that, hitting F4 puts the $signs in. And then table array is going to be this table here. So we need all the way over. And you can see I've numbered the vertical columns here. So FX is column 14, FY is column 15, FZ is 16. We're going to anchor that as well. And for FY we wanted 14, and then range we always want to pick false. And we can just copy paste this over to our other ones. And we'll have to adjust these for columns 15 and column 16. Perfect. Now when we change this number, It's not filled in yet, but these ones should update for that load case. Next, we have to calculate our moments for our applied forces. These ones are a little tricky because we have a 3x3 matrix, and each fx is going to create a mx, my, and mz, and fy is going to create an mx, my, mz, and same thing for fz. So we just have to be careful here. We're going horizontal, and we're going to do equals. We're going to do cross product, and it's r, which is the distance from our moment center to our applied force, and we're going to cross that times our force vector, which is fx here. And we can hit enter, and we can just drag this down. Perfect. So now we need to throw everything into our large matrix here. I've copied in our MathCAD image here. So I just want to remind you how in the first column, the top three here are the unit vector A, whereas before these are organized horizontally, we need them vertically here. So all we're going to do is transpose that. And then this is our unit vector for B, unit vector for C, unit vector for D, and then we have our alternative names here. So we're going to highlight the three of them, and we're just going to transpose. We'll go up, select this, and Control-Shift-Enter. And there we go, it's just transposed in here. Now we can do the same thing for these, however the fastest way is actually if we just transpose the whole thing. And Control-Shift-Enter. And here we go. Now for our moments, these ones are going to be a little bit slower. We are going to have to transpose, and we're going to do a cross product, and it's going to be r cross a. So we have our unit vector r, and we're going to cross it with our unit vector of a. Close our brackets, and then Control-Shift-Enter. These ones, unfortunately, we can't do them all at a time. We have to do them one at a time, which is why I've magically filled in the last ones for us, just to keep things moving. So we're going to transpose, cross product, r, which is here, for the second one. And we're going to cross that with our unit vector for B. Close our brackets, Control-Shift-Enter. There we go. And then our last ones are already filled in for us. And then finally, for B, so sum of forces in X equals 0 is this. So we need our negative Fx applied, as you can see right here. So this is just going to be negative Fx. This one's going to be negative Fy. And this one's going to be negative Fz. Now for our moments, we need to sum up the moments, the mx. So we're just going to equals sum. It's actually negative sum, and we're going to take our three mx's here, and that doesn't need to be an array equation, and then we'll just do the same thing for the other two. Perfect. Now if we keep going down, we need to determine what our fx, fy, and fz. And like I said before, we're going to start with our accelerometer data, or estimates on top of what we've seen. That's going to define all of our load cases. So we have max braking, max turn, max speed. That's only for an aero car. Acceleration, combined loading, which is our example shown in the spreadsheet in MathCAD. Our example shown in PowerPoint. And then we have our more extreme ones here, as well as inside braking, inside turning with no weight transfer, and reverse braking down here. I do have columns here, calculate aero. We're not doing those today, but I just want to remind you if you do have it. So first thing, we're going to calculate our lateral weight transfer using this formula here. And I'm going to hit F4 to put our dollar signs in. Lateral acceleration. And we're going to have to multiply that by 9.81 to convert G's into joules per second squared. Multiplied by height of gravity, and then we'll anchor that one, divided by our track width. Anchor that one. And we're going to do pretty much the same thing for longitudinal. We just have to change those two and use wheelbase instead of track. Next thing we'll be calculating is our Fz applied, so that's all the way over here. and we're going to take the mass of the car plus driver times 9.81 divided by 4 plus lateral plus longitudinal divided by 2, and then our FZ percentage, which is this formula here. It's really important that we put all of our proper dollar signs in when we just want to drag everything down at the end. Now, so for our FX of the vehicle, we're going to take, oh, the equation's not here, we'll start with Fy, mass of the car, 4, lateral acceleration times 9.81, and we can do the same thing here. And finally, we can determine our Fx and Fy. Awesome, now we can just copy these all the way down. Again, I just want to reiterate that we have a major assumption here on the forces of our tires. So now we're just going to manually modify some of these. So for maximum bump, we're just going to manually do the weight of one corner of the car times however many G's we want vertically. So we could say 5 G's vertically. And for inside no weight transfer, we're just going to manually set the lateral weight transfer to 0. And for reverse braking, this is on the front of the vehicle. In this case, we will have, we can assume 0 weight transfer longitudinally, which is the conservative case. There. For the rear, this is for the rear of the car. Obviously, you want full weight transfer, and that'll end up with a lot more load on rear wheels. So this is the front of the vehicle, so we won't have any adjustments because the front wheels do not have drive shafts attached to them, so they'll never be torque going through them. But if we were doing the rear, then for like maximum acceleration, in this case, you know, we'd add in 250 millimeters, and then in this case here, when we go back up to where our locations of our moments are being applied, for the Z component of Fx, we can do equals our original one plus, and we'll do a VLOOKUP from our load case number, table array, column number was 17, and we always want the last one to be false. And then that would adjust it for us. Just because we're down with the front, we're going to manually set that back to 0. Now we can get more into our load cases here. So if we wanted to look at any one load case, we can just adjust this one. And now we can solve. So we're going to select all these. We'll do it's matrix multiply in Excel, and it's going to be M inverse, and the numbers here are useless. it's going to be this is matrix inverse of matrix A multiplied by matrix B. And again, the order of these is very important. And we're going to hit Control-Shift-Enter, and there's our forces. Now, to solve for all of them, we will just do a data table down here, and for all of our load cases, and we're just going to put in transpose of this. This is a requirement for the data table. So these are going to be our outputs that are going to show up in everywhere in our table, and these are going to be our inputs, which are our load case numbers for our data table. And then we can go data, analysis, data table, and our column input will just be our load case number. And there you have it. So now we can look at our highest operating forces, which is all we really care about. And note that tension is negative. So we're going to be interested in the minimum for all of our tension load cases, and we'll also put the number 0 in there because these are all compressions, so we won't actually care. Things get a little slow once we turn the data table on. We can speed things up here by going File, Options, Formulas. We'll do Automatic Accept Data Tables. And you'll have to note that you're going to have to press F9. If you hover over it, you'll have to press F9 to recalculate the data sheet or the data table. And just don't forget to do that. So we now have our highest operating forces here. For buckling, we're interested in compression, so that'll be max. And really we care about any load case here. We'll put in 0 in case they're all negative. So we can copy that one over. Compression is the same thing, so we can just copy this formula. And then for tension, tension is negative, so we're going to use min. We'll also put a 0 in there. And then we just drag these 3 across. Now, if we had done the common mistake of just using the single push or pull rod and not looking at all the other arms at the same time, then we'll see how far off we'd be. So if we had a applied FZ here, and then if, and this is our, pull rod coming at this angle here, and if we broke that up into a Z component and a Y component, we're just assuming 2D for now, and this is the force in our pull rod here. And if we just assumed that the FZ component of our pull rod was the same as the FZ applied to the tire, then all we would be doing is mathematically, it would just be the force, FZ force, and then we divide it by the Z component of our unit vector. So that would be divided by this number here. And if we do that, then you can see this is the wrong force that we'd be getting. And if we calculate here, so these are our wrong forces, then we have our correct forces in this column. And then we can actually look at what percentage, how much larger or smaller our actual force is than our wrong one. So you can see here, like we're getting up to, we have 200% times. In our largest load case here, we're actually at 175% times. So this is in our worst case. So I mean, if you'd calculated it this way and you put a factor of safety of 2 on, you're quite close to failure. Yeah, even after your factor of safety. So this is why your pull rods could break if you did it the wrong way. From here, we can calculate if we input our column properties. So these are all in inches. That's typically how the tubes come in North America. So we have an outer diameter and a wall thickness. And then we can calculate the failure in fatigue, as well as in tension, compression, Euler buckling, And then there's this combined buckling compression as well. And then looking at the failure loads here, and then comparing to our actual highest operating loads, we can calculate factors of safety for our 6 tubes. So I'm not going to go through the failure modes today. If you're looking for a reference, then I can suggest Shigley's Mechanical Engineering Design. And that'll conclude the Excel portion. Back in PowerPoint, I just want to point out that actually in Excel, since we know the length of the magnitude of the forces and the unit vectors, we can actually plot the forces. You can either do a chart or as you can see here, I've programmed something in VBA that'll help us visualize our forces. I'll probably put the VBA code for this on my GitHub. However, I don't think there'll be a walkthrough of how to use it anytime soon. If you're trying to look through the code, one thing I'll mention is that I do use named ranges a lot, so you'll have to work those out. And here you can actually see that our pull rod, which is this arm here, is actually increasing significantly because of our upper control arm is at a very low angle. And as these two become more and more in plane, the forces are going to get higher and higher. And this is one of the reasons why we can't just simply take we can't look only at the pull rod forces using similar triangles because these upper control arms are increasing that force very significantly. We can also look at an inside wheel, and you see in this case the two aren't fighting each other as much. One thing to note is in most situations the lower control arm almost always has higher forces than the upper control arm. And then finally we can do a side view, and this is in a 1.9G braking, and we can see how our lower control arm has a much higher force than our upper control arm. That concludes the presentation. I want to thank you very much for watching.